purpose of this lab was to observe an object moving at a constant velocity and comparing it to a computational model which both used the properties of Newton's second law. In order to do this, I recorded a video of a ball rolling and tracked its position over the course of 0.8 seconds. As per the coordinate axes placed on the experimental model and tracker, the object moves in the positive x direction. The parameters in this experimental model were time and position, giving velocity by the slope of the graph. Measurements were calibrated to be 0.065 meters or 6.5 centimeters as the diameter of the sphere, which was the object in motion. Although the model showed perfectly constant velocity, this was not possible in the experimental model. This is because of microscopic grooves on the ball and also different forces such as gravity and friction acting upon it. The friction force eventually slows down the speed of the ball, so I made sure to clip out the beginning and ends of the video where the speed may have been skewed. The ball.pause variable is set to be the vector 0.070600 because this was the position of the ball at time t equals 0. The ball.vel variable has vector 3.57900 because the ball is moving in the positive x direction. Some velocity equations are the average velocity is equal to delta r over delta t, which is the change in position over change in time. Instantaneous velocity is calculated as the specific velocity at a specific point in time, which is the position at that specific instant divided by the time at that instant. The origin was defined to be vector 0.13700 centimeters. The distance traveled was 3 centimeters, and the elapsed time was 0.8 seconds. As per the average velocity equation, the average velocity of the experimental model was 3.579 centimeters per second. Now we know where the vector 3.57900 for ball.vel comes from. The time step or delta t variable for this model is stated to be 0.033 seconds for concise results. After running the code, here is the result of the computational model. The code follows a while loop for 0.8 seconds, the length of the tracker video. In the while loop, the fnet variable is set to vector 0 because this is a constant velocity motion problem and acceleration is 0, and by the use of the formula f equals ma, fnet is also equal to 0. Another derivation of Newton's second law is the momental principle, which is Vf equals Vi plus Fnet over m delta t, which is also derived by delta P equals m delta V. Since there is constant velocity in the experiment, there is no acceleration as defined as a change in velocity, while velocity is defined as a change in position. In this experiment, mass did not play a vital role since Fnet equals 0, so the entire value in the parentheses would be equal to 0 and be cancelled out. Next, the ball.vel variable is defined as the Newton's second law, which was shown previously. And finally, the new predicted position after each time set is denoted by ball.pause. The trail of the object has been then tracked by a successive time step by the line t equals t plus delta t and trail.append. After retrieving data from the computational model and the experimental model, this is the data extracted. Then, after plotting the two models for position versus time, the R value, or correlation coefficient, is 0.999. This value is a range of -1 to 1, and since the correlation coefficient is so close to 1, this means there is very strong positive linear relation between position and time. Although the R value does not relate the two graphs, it does show the obviously positive relation between position and time. As time increases, position also increases. The slope of the graph is the average velocity as calculated earlier. For the experiment, this was 0.375 centimeters per second, and for the computational model, it was 0.3579 centimeters per second. Some final thoughts of the lab are: what if the axes were flipped? The magnitude of the speed would stay the same, but the direction would be negative instead of positive. Secondly, is it possible to say how many pushes and pulls are added together to give a force in the observed case? Because a force is defined as the amount of pushes and pulls on an object, in this case the pushes and pulls are equal and therefore cancel one another out, leaving Fnet to be equal to 0.